Okay. So I'll start the chat box here. All right, starting a new chapter today with you, and this is mineral analysis. So like always, we'll go with why is it important to analyze minerals? What is the relevance of minerals in food? Labeling, very good. What do you know what minerals are on the label? Potassium, sodium, and calcium. Not necessarily zinc. Zinc would be added if, let's say, a cereal box, you can see all the fortification. So if a cereal has been fortified, let's say with zinc and iron and iron was forgotten. So it would be calcium, iron, sodium, and potassium. But then if we have fortification of magnesium, zinc, iodide, you'll see that also listed sometimes on the label. Okay, so other than labeling, what else, where else do you, okay, determining diet adequacy, yes. Exactly, understanding how minerals are affected during processing. Can somebody give me an example there? A processing example that might impact the mineral content.
If you were washing some food, you might dissolve some of the minerals in that, and you might have to add them back in.
Yeah, you might lose some minerals in washing, but there is a very common one. While vitamin is not a mineral, it's a good example of impact of processing on vitamin C. But if we're talking minerals specifically, not vitamins, minerals are different. So yeah, cooking, we can lose some minerals during cooking. What I'm looking for is a simple example that we are all familiar with is production of refined flour. So when we mill the flour and remove the bran, we remove quite a bit of, let's say, zinc, iron, magnesium, copper. So some of these essential minerals are removed. Therefore, there is that requirement to enrich the flour with what has been lost due to refinement. So that's where the word enrichment come from, is to bring back what was lost. Another example of processing, let's say you are producing acid produced cottage cheese. So you're producing this cottage cheese and you're reducing this the acid, reducing the pH, so you have high acidity. Under high acidic conditions, some calcium that is bound with casein is leached out into the whey and can get lost. So that you would have a loss in calcium due to processing. So another importance is, I would say, also fortification. Sometimes, like we talked about, yeah, fortifying the cereal with additional minerals. Sometimes your orange juice is fortified with calcium. So fortification is adding minerals that hasn't been there originally, like fortifying the salt with iodine, which helped a lot with goiter disease. So that is fortification, which is different than enrichment. Sometimes you hear enrichment, sometimes you hear fortification. So these are two different terms. One is meant to put back what was lost during processing, and the other was just to fortify. That means you add something that wasn't there or increase the amount of a certain mineral that wasn't there. We talked about processing effect a little bit. Water quality is very important. Have you heard of hardness, water hardness before? So yes, so hardness, that means high concentration of calcium and magnesium in your water. So if you're producing a beverage and you want it to be clear and you use hard water, you end up having some cloudiness in there that you don't really want. Let's say you are using, you're pickling, you're putting some cucumbers and then the water in there, or you're just storing your vegetables or washing your vegetables in water, and you get high hardness or high calcium magnesium in the water, then your vegetable is going to wilt. Some of the water is going to go out by osmosis due to having higher concentration of ions in your water. So water quality is very important. That's a big part of testing water quality is determining the amount of minerals or the hardness for calcium and magnesium. Okay, this is just showing our older nutrition label where we had sodium, we didn't have potassium, we had calcium and iron. And the newer one, we had potassium added to it due to the health benefits of having a potassium for muscle movement and other health benefits. So, okay, so the minerals are classified based on how much we need them. So you have the macro elements and then you have the trace elements. So macro elements are those elements, that minerals that we need at concentration more than 100 milligrams per day. So that's why they're called macro. And trace elements, we need them in milligrams to micrograms per day. And then, of course, there are the toxic elements that we don't want them to be present in our food, such as lead, mercury, cadmium, aluminum. So there are different analytical methods. Of course, we talked about AA and ICP, inductively coupled plasma atomic emission spectroscopy, and its main function is to measure mineral elements in food samples and water and soil. But it's mostly used when you have a lot of samples and a lot of minerals to test. But let's say I just want to measure salt content in few samples. So I can do a titration, a more titration, for example, MOHR, more titration. We'll talk about it in a minute. Or if I want to measure hardness in water, I can do a titration method. Sometimes you just want to measure phosphorus amount. We can do that using colorimetric assay. We'll talk about that. And sometimes you just want to get a concentration really quick in few samples that you can actually measure the concentration with standards and in your sample using ion selective electrode. So it's kind of like a pH meter, but your electrode, instead of detecting change in potential due to hydrogen ions, it would be selective for chloride or selective for potassium and stuff. So the nature of the analysis may or may not require ashing. For example, if we're measuring hardness in water using complexometric titration, you don't need to ash the water, obviously. You can do it directly in your water sample. And sometimes you also measure salt directly in your sample without having to ash it first. And that's, we can do more titration, for example. And we'll talk about these different titrations here in a bit. If we want to measure our set of minerals, we already know that we need to ash the sample for AA or ICP. And for colorimetric, we need to remove matrix interferences. So often you ash your sample and then you solubilize it and you prepare it for colorimetric assay. And in most cases, also for the ion selective electrode, we also require ashing. So consideration with respect to sample preparation. So during sample preparation, we want to avoid, what do we want to avoid? During sample preparation, one important thing, loss of minerals, loss of, yes, through volatilization, yes, and also contamination is another thing that we want to avoid. In terms of interferences, sometimes at different pH, you have different ionization, you have sample matrices that may interfere. If we're doing absorption-based detection, you might have reagents that have contaminants in them, mineral contaminants. So in this case, we always run reagent blanks and also run standards under the same conditions. So that's basically what we talked about. So looking into hardness of water. So the most common method is EDTA complexometric titration. You can either do the titration yourself, or we can get something called AquaCheck tester, which has embedded reagents in them, similar to the reagents you use in titration. So it's very simple. You have the reagents in the strip and you just dip it in water, monitor change in color, and there would be kind of a range for the different color intensity to get an approximation of the concentration or the hardness of water. Now, what's the principle behind the titration? Here it is. So EDTA, it complexes with minerals or positively charged elements. So calcium and magnesium can form complexes with EDTA. So what we do in the titration is we get an indicator that also complex with metal ions. However, the affinity of the metal ion to the indicator is lower than the affinity of the metal ion to EDTA. So EDTA has higher affinity to the ion. So what happens is if I have my sample water, let's say, has calcium, magnesium, I put my metal indicator in there. I add the indicator. The indicator chelates or binds to these elements or metal ions and then changes color. It goes from blue to pink. So that's an example here is the Kalmagite indicator. So once we add it to the water, it will bind the minerals and change from blue to pink. Then we put our EDTA in a burette and we start titrating. So when we titrate with EDTA, when the EDTA goes into the water, it's going to displace the ions from the indicator, and then the ion binds to EDTA instead of binding to the indicator. So you keep titrating until the last drop of EDTA takes all of the remaining ions that is bound to the indicator, and then the indicator changes color from back to blue, from pink to blue, because all of the ions now are bound to EDTA. Now, one thing is important here is to make sure that the pH is alkaline. The reason is that at acidic pH, EDTA become protonated. That means instead of binding with the positively charged ions, it's going to bind with the protons, H pluses, and no longer have the ability to bind to the metallic ion. In this case, that's why we run the titration at pH 10 or 11 alkaline, so that the EDTA has maximum affinity to the metallic, positively charged metallic ion. So that's the principle behind the titration, and that's the principle behind the AquaCheck test strips. So determining salt content, or usually we determine salt content by determining chloride and ACl, so we can follow the chloride reaction. What happens here is you have your salt and then you titrate, you put in the burette, you put your silver nitrate. So you have silver nitrate, so the silver ion plus, which is positively charged, will react with the chloride in your sample. The more chloride you have, the more you're going to titrate, and then you form the silver chloride. Now, we don't care about silver chloride here. What we care for is the change in color due to the addition of our indicator, which is the chromate indicator. The chromate will react with silver to give orange precipitate. So when all of the Cl has reacted, the next drop of silver nitrate is going to react with the chromate and give you an orange precipitate, and that's the end of your titration. It's very simple. We call it forward titration because there's no excess. You're just titrating directly with the silver nitrate and using the chromate as an indicator. Now, the Vollard titration is backward. And if you ask me, why do they have Vollard titration? I tell you, I don't know. They just thought of it backwards and depending on availability on the agents. So why is it backward and what does it mean? In this case, you have your sample with the salt in it, the Cl, and you add directly a specific amount of silver nitrate that is in excess. So you just say, I'm going to put 30 milliliter of silver nitrate in there, a specific concentration of it. Then the calcium that is present, the chloride that is present is going to react with the silver and give you silver chloride. Great, and then we will have excess remaining in the solution, some silver ions that hasn't reacted with any more chloride. In this case, we titrate with thiocyanate. So your burette here, instead of having silver nitrate, you have thiocyanate in there. And you have iron, ferric ion, as an indicator. So the remaining silver ions that no longer have any chloride to react with, we will be titrating with thiocyanate. When all of the remaining silver ions has been reacted, the next drop is going to react with the ion of ferric ion and gives you a red endpoint. So it is backward because if we know the excess, how much we added of silver nitrate to our sample, and we know how much reacted with this thiocyanate, the difference would be the amount reacted with the chloride. And that's how we would calculate. It's backward calculation. And we'll have a calculation example here in a little bit. So I see a question. Oh, a couple of questions here. All right, so first, for the forward reaction, what ions we are measuring for? For the forward reaction, we are measuring the chloride, and now at the end of the equation, number of moles of silver reacted with chloride equal number of moles of chloride. So at the end of the titration, you take the volume of the silver nitrate that, that we use to titrate and reach the endpoint and determine the number of moles of that, and that would be equal to the number of moles of chloride. And from there, you convert to amount of sodium chloride, because all is 1-to-1 mole in the chemical reaction. So now the other question, I realize, is there any policy from FDA that you need to follow for fortification? I'm not sure. For fortification, it's kind of like the, let's say for the cereal, we know how much we need of a particular of zinc, and we say we want to meet at least 80% of the requirement, the daily intake requirement, or I want to meet 40% of that. You just formulate per serving to meet that particular percentage. But you want to avoid adding excess, especially for minerals that could be toxic at higher concentration. Like, for example, fluoride. If you consume a lot of it, it becomes toxic. So you have to make sure that you don't exceed a certain amount of fortification if an excess of that particular element is going to be not healthy for you. Um, yeah, other than that, I don't think of anything else. Okay. So here's the test strips that we can use for determining salt. They call them the Quantab chloride titration test strips. So it is based on the more titration. So you have the same reagent and the same indicator. And then when you put that strip and when it changes color, you get, you have, again, a range of salt content based on the color indicator. It is accurate to kind of 90% confidence. And it's good for specific concentrations between 0.3 to 10%. So it is rapid. It is an official method that has been verified. Okay, this is just, again, recap questions for you to study from. Other methods other than titration, colorimetric method. One very a common method that we use with just measuring the reaction and the chromophore that is formed is phosphorus. So the sample needs to be ashed and then solubilized in acid-based solution. And in the presence of a specific reagent that will react with phosphorus. And this reagent is molybdenate reagent. So it basically gives a very yellow color when it reacts with phosphorus. And the more phosphorus you have, the brighter is that yellow. And then you would just have standards, phosphorus standards at different concentration. And then you just measure absorption and do a standard curve like you usually do and get the concentration in the unknown based on your equation, line equation. Ion selective electrodes. So basically, like I said, it's kind of like a pH meter, but instead of measuring the potential due to hydrogen ions, you measure the electric potential developed related to that particular ion of interest: calcium, sodium, chloride, potassium, fluoride. These are the common ones. You have electrodes for them. But this method is very much dependent on the sensitivity of the electrode to that particular ion. And also it is dependent on the ionic strength of your sample. So you want to run standards and you want to ensure that everything, all the other ions are constant and they won't impact the reading. And then only you change that concentration of that particular ion that you're interested in. You build your standard and standard curve, and accordingly you can get the concentration of the unknown. So this is what I said about having this similar ionic strength in the samples and standards. Sometimes your electrode may detect or may be impacted by other ions, so that causes about 10% error. It has very good sensitivity down to the 10 to the negative 6 molar, which is very good. However, the disadvantage here at lower concentration, with any pH meter, it might take a little longer time to stabilize to get the reading. The applications usually salt and nitrate in processed meat is very common. Quick looking at calcium content in milk, salt in butter and cheese, potassium and sodium levels in wine. These are very common applications for ISE. So now we're going to spend some time here on calculations. And this is important calculation for you to understand, and we'll go through that together. So I want you to take a few minutes thinking about it on your own, write up in your notebook. And Chrissy here, was it Kat or Chrissy last time that showed us her computer? She can write. Kat, was that you?
It was Kat.
Okay, so no pressure, Kat. Try to get it right. You're gonna show us how you did it. So just to give you a hint, you want to determine the number of moles of the excess silver nitrate. You want to look at your equation here. So you want to get the number of moles that you had originally put, which is 30 ml of 0.1 molar. And then you want to determine the number of moles that reacted with the remaining. The difference would be the number of moles reacted with chloride. And since they're equimolar, that would be equal to the number of moles of chloride. And from there, you need the molecular weight of NaCl, which is 58.5. Sodium is 23 and chloride is 35.5. So if you have the number of moles and you have the molecular weight, you can get the grams. Okay, so this is kind of a hint for you to move forward. If you have finished and you have any numbers for us for moisture or ash on dry weight bases, or even the salt, you can start typing in. Very good. Yes, Kat, you got all of those correct. Sam, you're off by a little bit.
I used exactly 58 for sodium chloride, so that's probably why.
Oh, okay. So it should be 58.5. That's more exact.
Mm-hmm.
Yeah. Good. Did anybody else, if you gotten any calculation, you can type it to get your participation points. Or we can give you a couple more minutes just to get participation points before, since Kat got it right, then she can walk us through this. I'm gonna have make Kat co-host so that she can share her screen. Kat is smiling. Okay. All right. Not sure how to get the salt content. Okay, Anastasia, we'll work on that together. Megan got the correct moisture and ash. We'll get to the salt content together. Anybody got to the salt content? Yes, Anastasia correct. Jean correct. All right, so a lot of you got the moisture and ash and got stuck on the salt. Does that sound pretty much it? Okay, then I'm going to stop sharing. Okay, Emily. Good, yeah. You can continue adding in your chat if you like your answers, and then I'm going to stop sharing. I stopped sharing. So Kat, can you walk us very slowly like you're the teacher?
Okay.
And
Can you all see the, sorry,
you want to share your screen?
am I sharing it? It should be just a white blank screen and I can,
Yeah, so you can go ahead and share with using the, like you did for lab, during lab.
okay, yep. Just give me a second. My pen just stopped working.
Oh yeah, I can see it now.
Okay. Okay, so I want to erase that. Okay, so you start with, you have 3 milliliters.
Can you come closer to the mic?
Sure.
Yes, this is good.
Okay, so you have 3 milliliters of 0.1 molar, that is Ag salt, silver nitrate. So to turn this into liters, you divide by 1,000. So you have 0.
That you have 30 milliliters.
Oh, sorry. Yes, you're right. 30 milliliters. I don't know why that all the way up there. So yes, that's 30.
Yeah.
So that is 0.003 liters times.
Oh, it's 0.03, not 2 zeros, right?
I thought it was, oh, sorry. Yes, you're right. Sorry, I'm messing up.
That's okay.
So 0.03 liters times 0.1 moles per liter. And then the liters cancel out and you get 0.003 moles.
Yes.
And then so that's how much of the salt, sorry, I keep saying salt, silver nitrate is going into solution and then it's reacting. And the amount of silver nitrate that's left over can be found by subtracting the amount of moles of the potassium thiocyanate from this. So to find the moles of potassium thiocyanate, you have 3 milliliters times 0.1 molar of potassium thiocyanate. And then you do the same thing where you divide this by 1,000 and you get 0.0003 moles. So now you can subtract these two values. So 0.003 moles, because we have a 1-to-1 ratio. And that equals 0.0027 moles. And then we want to convert that into weight. So we have 0.0027 times the molecular weight of salt, which is 58.5 grams per mole. And that gives us 0.1579 grams. And then we divide by our total weight, which is 25 grams. And that gives us about 0, and times by 100 to get the percent. So that gives us 0.6318%.
Perfect. Yes, keep your screen up for a second, and I want to see if anybody has any question on any of these steps. So let me open the chat box here to see Why is it subtracted? Yes, very good question, Anastasia. So if you remember the reaction at the beginning, you have your solution of that has the salt in it, your sample that has an ACL, and then you added directly to this solution, you added 30 milliliter of 0.1 molar silver nitrate. So you added, this is in excess. So some of it reacted with the NaCl. So some of the silver reacted with the Cl, and there was some silver remaining at the end of the reaction. So that remaining silver was reacted with potassium cyclocyanate. And the reaction here is 1:1 molar again. So 1 mole of silver reacted with 1 mole of potassium cyclocyanate. So at the end of titration, at the end point, you only use 3 milliliter of potassium cyclocyanate in this case. So that means the difference is the amount of silver reacted with the salt. Because what's left, if we look at the number of moles that we added of silver nitrate, the total number of moles is 0.003. And some of that reacted with the NaCl that are already present. The remaining reacted with 3 milliliter of 0.1 molar cyclocyanate. So that 3 milliliter is 0.0003 moles. So that's the amount of silver remaining as well, because it's 1:1 ratio in the chemical reaction. So the total amount of silver I had was 0.003. And the remaining I had that was titrated with thiocyanate was 0.003, 3 zeros. The difference is 0.0027. That difference was the amount of silver that reacted with the chloride present. And again, since it's 1:1 mole chemical reaction, this will equate 0.0027 moles of NaCl. Because again, there's one Na and one Cl. So the same amount of moles of Cl would be the same amount of moles of NaCl. So to determine the mass of NaCl, we take that number of moles and we multiply by molecular weight, because number of moles equal mass over molecular weight. We're searching for mass and we have the molecular weight. So we just multiply and the moles cancel and we get 0.158 grams of NaCl. If we divide that by the total amount of sample we started with, which is 25 grams, we'll multiply by 100, we get the 0.632 if we round up. Is that clear, Anastasia?
So if I'm getting this right, it's like because you add excess SCN, so you're gonna like, I don't know how to say it. It's like, it's just to correct for the excess SCN that's present.
It's not excess. You are titrating with SC, and like any titration, you know, you have the SC, the potassium cyclocyanate in your burette, and you're just titrating drop by drop, and the last drop it gave you the red point, you stop, and you look at your milliliters of how much you've used from that solution, and turned out you've used 3 ml. So 3 ml of 0.1 molar, how many moles, number of moles, is the 0.003. So that's equal to the remaining silver. After reacting with the salt, you had a remaining silver.
Okay, right? That makes sense.
And all of the equations are 1:1 mole. That's why everything equal each other.
Okay, thank you.
Okay.
How, oh, sorry. Pam, how can we be sure that all the chloride ions are coming from sodium chloride and not other salts?
Well, you always run a blank. So
That makes sense.
I did not include the blank here, but you definitely want to include blank.
Mhm.
But there's also anything coming like chloride from anything else from the sample would be also minimal, and that's why it's approximation. Everything in composition is approximation.
Okay, thank you.
Yeah. Any other questions on that? Well, thanks, Kat, for showing your calculations and with your cool screen. I wish I had that. That would have been really helpful for teaching. Um, anyway, any other questions via chat? If not, we have 3 minutes, but I can let you go and we will see you on Friday. No, what's today? Yes, Wednesday. We'll see you on Friday. Okay, you guys. Bye-bye.
Hey Pam, I had a question about the quiz grades.
Yeah, don't worry about this quiz grades. There is a something you're not supposed to see the grades, and you're seeing partial grade. The quiz has not been graded fully yet. For some reason, you are seeing your grade and you shouldn't be. I talked to Laura, or I talked to Fan to let Laura know to prevent you guys from seeing your partial grade, because you're going to go, what? I got 10 out of 30?
Yeah.
Yeah, no, don't worry about it. They are not officially released yet. I don't know, for some reason, some of you are able to see the partial grading. They are still grading, so they're not done. And I usually also review before we submit the final grades. So don't worry about it. I'll let you know when all the grades are final.
Great, thank you. That's a huge relief.
Yeah, okay. All right. Bye.
Thanks, Pam.
Thank
Bye.
you.